All right, welcome back again to just finished the section on inequalities. Today we're going to talk about now expanding the range of functions that we can talk about. Section 2.4 is more on inequalities, and again we're going to continue what we talked about in section 2.3 using those properties of inequalities, but now expand it out to quadratics, expand it out to rational functions, so we can find the intervals of solution for those types of functions. Also today we want to continue to talk about what does the solution mean to the original problem. In other words, what does that give us about the original problem? So let's take a look at today. Let's go take a look at our goals for learning. Again, section 2.4, more on inequalities. The first thing we want to do is expand the range of functions to which we can solve and talk about an inequality. And then be able to discuss what that means to the original inequality. And a couple examples we're going to look at just to talk about first originally. Give me a second to copy that down. So take out your graphing calculator or take out whatever you have available to graph with, and let's take a look at this first function here. We have x squared minus x minus 12 greater than 0. Now, this is kind of a dumb question, but when we look at this graph, do we want to find where it's above the x-axis or below the x-axis? Okay. Just so we know what we're looking at. So we want to find where this is bigger than 0, where this is above the x-axis. So let's go ahead and take a look at our graph here. And we have graphed x squared minus x minus 12. I'm going to actually, just to remind everybody, I'm going to switch this to a dashed line because it's less than but not equal to. So it's everything below the line but not including the line itself. So let's take a look at this with our function here. We want to find where this is greater than 0. So we see there's a couple points, probably close to -3, probably close to 4. And our solution, we want to find where it's bigger than 0. So it would be everything from -infinity to -3. But this part's not part of it because it's not greater than 0. Then from 4 on to infinity. Question to you guys, does it include the points -3 and 4 in that set? Now the dashed lines are kind of a cheat for this, but does not include the point -3, does not include the point 4. So as we think about what's our solution to this set, our solution is again going to be an interval. And for this particular one, the range of solution that would be true would be from -infinity up to but not including -3, and from -4 but not, from 4 but not including 4 all the way to infinity. So when we are solving these inequalities, we're finding that range of number that we could plug into our original equation to make that inequality true. Okay, let's take a look at a tricky one. Let's go back to our example. And actually, let's just take a second real quick. Questions on campus? Do we need to look at that one again? Let's take a look at the second one. Tricky for 1 point. X squared minus 3x. We want to find where that's less than or equal to 4. Less than or equal to 4. So let's plug that in. So I plugged into my calculator, to my graph up here, x squared minus 3x, that was what's on the left side. Now, easy one to make a mistake in. I will warn you, with most of your test questions and with most of your homework questions tonight, this is the type of thing you're going to run into. Most students will look at that, plug it in the calculator, they'll say, okay, here's my one intersection right there, and that looks nicely to be at 0, how convenient. And then I find one at 3. And right there. And okay, I look at that. Okay, I want it to be less than, so my solution is from 0 to 3. Why is that not correct? Why is that not correct for this one? Okay, what do you want it to be less than or equal to? And then give you a hint, it's not 0 on this one. Yeah, it's 4. So let's graph on there. Let's graph y equals 4. And our function will just be 4. Now, that's where we want it to be less than or equal to. There's obviously an algebraic translation that you could make in our original function to have it be 0. But there's where we want it to be less than or equal to. We want it to be less than or equal to 4. So just approximately looking at the graph, looks like that's from about, where is that? -1. Yep. And about to 4. Now, do we want the parabola to be less than or the parabola to be greater than? We want the parabola to be less than. So our solution set for this one would be any value of x between -1 and 4. Question to you, would it include -1? Would it include 4? Well, let's go back to our original question. It's less than or equal to. So by implying that equal sign, that means if it returned a value 4, it still makes that inequality true. If it returns that value, it still makes it true. So at the point -1, we get a value out of 4. That makes the inequality true. That's part of it. And for the point 4, that gives us or returns a value 4. So that's also in that solution set too. So let's write it down for this one. So for the solution set for the second one, we have -1 to 4 with brackets because the point -1 makes it true, because the point 4 makes it true. Remembering back to our first one, we had a strictly greater than. So our solution set for that one, we wanted it greater than, so we could go from -infinity. And just to remind you real quick, here's what the graph looks like. It was from -3, to 4, so there's 4. And we wanted it greater than, so it was from -infinity to -3, and from 4 to infinity. Now, either one of those intervals work. What symbol could we use to say we want the union of both of those make it true, and that's that U. So there's an example of our solution set. Again, what does this mean to the original problem? You plug any number in this range, you plug any number in this range, you plug it in here, makes the inequality true. This one, you plug any number including -1, 2, 4 into there, makes that inequality true. Stop and just check up for a second questions on campus. Now, the graph, again, is a tool to help us, but it's not the only way we find solutions. In fact, most of them we're going to solve out by taking a look at the algebraic way to do that. And our book has a unique method called test points they use for this. So we're going to do the first example together, and then we'll take a look at what that means to the graph and look back original. So our first problem here, we have x squared plus 4x plus 3 is less than or equal to 0. And we want to use test points to find the intervals of the solution. Now, what are test points? And there are a couple different ways to explain it. Your teacher might have a slightly different one. What I think of test points, they would make the original inequality true if it were equal. So we set up the original function, and we had x squared plus 4x plus 3 less than or equal to 0. What if we had x squared plus 4x plus 3 equal to 0? That seems like a silly question, but how would you solve that? Okay, we could factor it. We'd have x plus 1, x plus 3 equal to 0. So that gives us a solution of x is equal to -1, x is equal to -3. Now, what these numbers give us, they give us intervals that we'd have to look for a solution. This is the number that gives us out 0. This is the number that gives us out 0. If we look at a number line, look at 0 in the middle of it, we're looking for the interval that this solution holds true in. We have -1, we have -3. Now here's the question. Is the interval solution between these two numbers? Is it from negative infinity to negative 3, from negative 1 to infinity, or some combination therein? So what we have to do is we have to take these numbers and use them to test out what solution we're going to end up getting, or where the intervals are. So what we're going to end up doing is we're going to test the numbers in these ranges to see which one gives us the value that solves our original equality. Remember with this one, we want x squared plus 4x plus 3 to be less than or equal to 0. So let's set up. And I'm going to follow exactly the way the textbook does for this. Your teacher may or may not have a way of doing this. I hadn't done it before I taught out of this Cohen book, but it actually ends up being a very clear way to find these solutions. So let's make a table. I do add one thing to this, though do note, Cornerstone teachers, I add a dashed line where your book has a solid line, but just from having taught this a couple times, it helps students understand what they have to do with it. So the first one, I want the intervals I have to test. And the intervals I have to test are from negative infinity to negative 3. Now with that, you'll note, negative 3 is part of the solution for this one. I include that negative 3 because you don't want to test negative 3, which would be part of that interval. If you test negative 3, of course it's going to work. So the second part, I put negative 3 itself. Then the next part is from negative 3 to negative 1. Then the point negative 1. Then from negative 1 to positive infinity. So those are the intervals that could possibly be our solution for this problem. We'll see which one ends up working out for it. And then we're going to choose a number to test. Test number for the interval, which I suggest trying an easy one. Then what are we going to do with that? We're going to plug it into that factored form that we have. We're going to plug it into x plus 1. This is where I put a dotted line because we're going to then multiply it by what x plus 3 gives us to give us what the product of x plus 1 times x plus 3 is. Now, students do note, when we're looking at these three parts right here, we're only interested if they're positive or if they're negative. How positive they are, how negative they are, doesn't matter because any positive times any negative will give us a negative, regardless of how large the quantity of those two numbers are. So let's pick a number first between negative infinity and negative 3, and an easy number to test would be negative 4. This interval from negative 3 to negative 1, easy number would be negative 2. And then from negative 1 to infinity, easy number to test would be 0. Note, for right now, I'm going to ignore negative 3 and negative 1 because we're going to note that when we come back and find our solution. Okay, so let's test. We plug in negative 4. Negative 4 plus 1, does it give us a positive or a negative? It gives us a negative. Plug in negative 4, x plus 3, is it a positive or a negative? It's a negative. Then we multiply a negative by a negative, we get a positive. So, let's ask a question real quick. Because that gives us a positive out, would that be part of our solution? Or would that not be part of our solution? Well, let's go back to our original problem. We want it to be less than or equal to 0, so unfortunately, a positive number is not less than or equal to 0. When you plug in negative 3, we already did the work. When you plug in negative 3, what do you get out? You get 0. So is that part of our solution? Yep, because it's less than or equal to. Plug in negative 2. Negative 2 plus 1 gives us a negative. Negative 2 plus 3 gives us a positive. And a negative times a positive gives us a negative, which is actually good for this situation because we are looking for something less than or equal to 0. Negative 1, if we plug that in, that's 0. Negative 1 to infinity, we're going to test 0. 0 plus 1 is positive. 0 plus 3 is a positive, so that gives us a positive. So where is our solution? Our solution is in this range here. And how do we write that? We're going from negative 3 to negative 1, including those points. So from negative 3 to negative 1.